condense into the same matter wave shaped state. And so what this does, there was a big fuss about it at the time, because this magnifies the quantum nature, this matter wave nature of the atoms up to the macroscopic scale. And it turned out that the gaseous Bose-Einstein condensates could be easily manipulated. They were long-lived, and so they could be easily probed, and they could be controlled for different applications. And so here you see this picture here. This is all the atoms look like that. They're all the size of the whole cloud. Okay, so maybe it's hard to get your brain wrapped around 1 million atoms, all the size, 4 or 5 orders of magnitude larger than they would be by themselves. So this, because that's like 100 micrometers across, essentially. So it turns out that there have been, there's a bunch of applications related to these atom circuits. An atom circuit is always going to involve a Bose-Einstein condensed gas, in the case that we're studying. There's a bunch of different applications relating to precision navigation and metrology and quantum information that people envision implementing with these kinds of systems. And there's been an enormous advance in all optical atom trapping technology. 10 years ago, there was a sea change, and there was 4 years ago, there was another sea change, which I'm going to tell you about in just a second. But if we want to use these systems as quantum sensors, then it's going to require us to understand at the quantitative level, understand how they behave. Nope, that's the wrong way. This is kind of unintuitive. Or I'm just stupid. Could be one of the two. Okay, here we go. So let me say a couple of recent advances that have occurred in the this new field is called atomtronics, so as opposed to electronics. And so there have been two important things in the last couple years. One of them is the ability with these things called digital micromirror devices to manipulate. Essentially, you can now take these DMDs, which you can buy on Amazon, and you can put them in your laboratory. Since they're used in digital light processing, so they're now a commodity item, so they don't cost that much. And you can put them in, and you can use them to create light potentials for the atoms. And so in this case, you can make, now with the DMDs, you can make potentials that have arbitrary space and time dependence. So here's an example of, you see right in there, that this little red streak in there, those are the atoms. Oh, I should say one more thing, because sometimes I just take these things for granted. If you shine light, and actually this was kind of what was the subject of the Art Ashkin, who won the Nobel Prize just the other week. If you shine light on an atom and you tune the light to the blue of an atomic transition, then this light will repel the atoms. The atoms will try to seek the low intensity. And if you shine light that's detuned to the red, then the atoms will try to move towards the regions of high intensity. And so what you've got here is two blue detuned light sheets. And the atoms are trapped in between, so that keeps the atoms from going up and down. And then you can take your DMDs and you can shine them. You can essentially make an arbitrary space and time dependent potential in this plane in between the two blue detuned light sheets. And so that, that is a capability now that like dozens and dozens of labs across the world have. And it's something that they've only had for the last 3 or 4 years because of the advent of these DMDs. The other thing that happened was that somebody developed a way of forming these condensates with a number of atoms that's below the shot noise limit. So that's 1 over square root of n, where n's the number of atoms. So, or it's the square root of n, excuse me, number of atoms. So typically there's 1 million atoms in a condensate. And always before, when they would make a condensate, they would do something to it. They would image it, which would destroy it. And then they would make another one and then do something else to it. And they would do this over and over again. But from shot to shot, the number of atoms, the fluctuation in the number of atoms was plus or minus 20%. But now, if you can do this below the shot noise limit, if you have 1 million atoms, then the fluctuation is square root of 1 million, it's 1,000. So you can, every time you can make something where you're fluctuating by 1/10%. And so that's a tremendous, especially for applications in metrology, that is a tremendous advance. And so as far as I know, nobody has both of these things yet, but it's just a matter of time. And when that happens, I think that there's going to be a revolution in these kinds of atomtronic systems. Okay. So here's the atomtronic system that we're talking about. I showed you 2 blue detuned sheets, but here. But you could also have a single red detuned sheet, which would suck all the atoms into the plane of the light sheet. And so here, that's what's been depicted here. This is a red detuned light sheet. And then you can have an arbitrary time and space dependent potential in the plane. And so the potential, and so to make an atom circuit, the potential that we're using is one that's a channel that may have some arbitrary shape that the atoms will sit in, so that the potential is 0 here, but then there's a ditch that goes along in some pathway that has a lower potential, and the atoms will sit in there. And so the ones that the potential that we've chosen to study, I call the racetrack potential. It's like 2 circular end caps with 2 straightaways separating them. And in this case, if you make the length of the straightaway 0, then that's just a ring. And so this is, I don't know if I mentioned I'm a theorist. So nothing I do, is actually true. Okay, just so that, just as a caveat, So, okay, so we want to make flow in our atom circuits. So we can imagine now that we take an ultra cold gas, and we put it in this potential, which looks like that. In a couple of hours, I'll get the hang of this. And where this ditch that I was talking about looks like that. And then if I cool the atoms down and form a condensate, they'll sit in this racetrack potential. And then what I want to do is I want to create flow, because if I'm going to have, just like in an electric circuit, I need flow, I guess it'll be that way. If I have flow of electrons, the same goes for my atom circuit. Here I've drawn some other stuff, which I'll explain more about in a second. But I say here smooth. I need to have smooth flow for most of the applications that have been envisioned. And so we're also studying quantum turbulence, but that's another talk. Hello. Yes. So let me give you an example. One idea for an application is to make a rotation sensor. So you can imagine, and so this is a cartoon picture of how an atomic rotation sensor might work. There's lots of stuff that I don't know how it works and what will happen, but I've chosen to neglect that. And so it would be a cycle that looks like this. And this all is possible because of these DMD devices that, so I make a condensate so that BEC is Bose-Einstein condensate, just in case. I just take that for granted. You do something like stirring to create flow, and then after there's flow, I'm going to distort the potential to, instead of being just this racetrack thing, I'm going to add, in real time, I'm going to add in a ring like this and maybe add some barriers here. This is the kind of thing that would make it look like a DC Josephson junction, which could be sensitive to rotation. So if you were to do this whole thing on a rotating platform, you would get different behavior than if the platform weren't rotating. And so then you would make your measurement, whatever it is, and then you turn it off. You make another one, and you would just cycle through this. And so it's clear that an essential component, if you were going to have something that worked like this, was to be able to make flow reliably, smooth flow on demand. And I also would like to mention that the flow that's possible is quantized, okay? Because these atoms are, this many particle system is made up of a bunch of atoms that all have the same single particle wave function. And that single particle wave function has to be single valued. So if I start and look at the phase of it somewhere over here, and I trace that phase around a closed loop, the accumulated phase has to be an integer multiple of 2 pi. Otherwise, the wave function will have a different value, and it can't do that. So that's what we're going to study. And so we're going to study it in this racetrack potential. And so can we make an atom circuit like that with smooth flow? And now there are a bunch of ways to create flow. We can, so I'm just going to quickly say we can modulate. It turns out that we can modulate the interactions between the ultra cold atoms by putting on an external magnetic field. So that thing called a Feshbach resonance. We can even change them from being repulsive to being attractive. And so the figure of merit for that is called the scattering length. And so we can make it spatially dependent, which would change their interactions. We could tilt the path of the atom circuit. We could do phase imprint, or we could stir. And so when I say stirring is the one we're going to look at. And so basically, if you want to think about what I'm talking about when I say stirring, I mean I'm going to take a laser beam. I'm going to put it in. Let me go back. Laser beam. Stick it in there and stir it around. If I make the laser beam blue, not like this, but if I make it blue detuned, it'll push the atoms out of the high intensity part, and that'll just be a stick in water. So we first started studying this at 0 temperature, and so let me. I have to tell you, I left out the slide that tells you what the basic model is. At zero temperature, basically, we say that all the atoms are in the same single particles, have the same single particle wave function. And so the many particle state is just the Hartree, it's the n-fold product of that single particle orbital evaluated at the coordinates of each of the atoms. And so if you use a variational principle to ask, make that my trial wave function and ask what equation does that single particle orbital need to obey, it turns out to be something called the nonlinear Schrödinger equation. So it looks just like the regular Schrödinger equation, except it has another term that is proportional, where you have a potential term which is proportional to the density. So there's actually a cubic nonlinearity in the equation. And so in this field, we call that the Gross-Pedievsky equation. And we can solve that time-dependent Gross-Pedievsky equation or time-dependent nonlinear Schrödinger equation in order to study the behavior of what happens when we put a stick in. And so in this model, the whole system is at zero temperature. Okay. Does that bother anybody? Does anyone have a problem with that? That zero temperature thing? Okay, then. So since nothing's really at zero temperature, but we figure, and actually this turns out to be a wildly successful model for condensates that are made as cold as they can possibly make them. So it's not at zero temperature, but the temperature is probably 50 nanokelvin. That's pretty close to zero. And so it turns out that the approximation of zero temperature for the behavior tends to work pretty well. It doesn't always work. Okay, so the first thing we tried, just to give you an example, we wanted to make flow. So the first thing we tried was to make something called a peristaltic pump. I'm not sure. It's like here. So here's our potential, and then we add this elliptically shaped paddle, which is centered on one end, and then it rotates around. I think I might have to. Yes, I have a fair number of these movies. So, okay. Let's try this. Go back. Well, let's just say that this is still too far. Yeah, there we go. So you can see here, this shows the optical density at in fact, I'm going to do this. No, that won't work at all. Never mind. Here, I can do it here. I see. Okay. Wake up. Okay. Here, I can look at it here and do it, I think.
I don't think you needed to play though.
Well, it was because it's on a different screen, I think. Yeah, there. Push that arrow there. Okay, this is what you get. Okay, there might be flow in there, but it's not smooth. So let's go on to this one.
Gotcha.
Oh, okay. You're going to have to stand there forever because I have a bunch of movies. Okay, so here is a much.
What about this one?
Yeah, you can do that one too. So we tried slowing things down. So at first we stirred it fast and hard, and weren't surprised that it wasn't smooth. And then we successively tried I'll get the hang of it in a minute. Yeah.
Right there. Look.
There. Okay. And you can see now that we got something that's a lot smoother. This is the optical density, but it's still not, it's not smooth. So what we did was we decided, we knew that this was we already knew that this was possible for ring condensates. Come on. Here. And so we had already done a previous project where we were able to stir a ring, and they had also made rings in the lab and stirred them and made flow. And so I put this in because I want to show you that, so need something that, is it that way? Yeah, okay. So here, in order to, oh, good. In order to know whether you have flow, you have to look at the phase of the wave function. So wave function is a complex valued quantity that has a modulus and a phase. And this phase, the velocity distribution for anything that follows the Schrodinger equation or the nonlinear Schrodinger equation is the gradient of the phase. And so you can see here that I put this one in to show you, because if you look at the density, I'm getting better at this. If you look at the density, you really can't tell that this is flowing. And the way you tell is by looking at this. This picture shows you the phase at each point in a cut through of the z-axis. So you've got this thing in a horizontal plane, and there's a ring around here, and the condensate looks like an inner tube or something. And I'm cutting through the z equals z, this is z equals 0, and I'm showing you at each point in the 2D plane the value of the phase encoded as a color. And so you can see that here's where the condensate is. This is the density. And so it's actually it's actually thicker out here, but you can see that if you start here and so this is 0, and that's 2 pi. So blue would go up to red, that would be 2 pi, and then because it only allows 0 to 2 pi, it drops back to 0. So it's 2 pi, 4 pi, 6 pi, 8 pi, and if you divide that by the circumference, that'll give you the gradient, the azimuthal gradient of the velocity. It'll give you the component of the velocity in the azimuthal direction. Okay? So that's what we're going to look at to know whether we have phase at all, whether we have flow at all. Okay, so after failing with this elliptical paddle, spectacularly failing, it was really great. We tried this out. We went back to here, there. So now here's the same thing for stirring a racetrack. Great, that didn't work. Now, and the thing is, when it disappears, it goes back off into the ether, so you have to come back and find it again. There. So why didn't that? There. So here you can see this is the paddle, this is the barrier that's stirring it. And you can see that you can't really tell anything with the density. Now let's look at the phase of this. Okay. And this shows you, this is this is time. Each frame is advanced in time, and you can see that once it gets past frame 38, it'll be finished stirring. So what we did was we were always stirring, but if you think about it, sticking a laser beam in there, you're stirring it, but the brightness is 0. And then I crank and turn up the brightness, it increases the potential, the energy height of the barrier, and then it goes back down to 0. And then we wait and allow it to evolve after we finish stirring, just to make sure that the flow that we get is persistent. And so we found that this works great. And so what we decided to do, since we wanted to know how much flow would we get for stirring under lots of different conditions, and specifically, we're interested in varying the strength of the barrier, the paddle. That's the same thing as making the laser that's doing the stirring brighter. The stir speed, so stirring faster or slower, and also for several different geometries of the racetrack. So everything from the ring, where this L parameter is 0, up to something where it's highly elongated. And okay, so so then for each, so we did a bunch of simulations using this GP equation, and every time we did that, every time we stirred, we evolved for 4,000 milliseconds. So we ramp up the barrier over a first 500 milliseconds, leave it on constant for another 500, and turn it off over a further 500, and then another 2,500 after that to see that it's persistent. But which seems like a little bit of overkill, but we want to leave time to simulate the operation of actual atom circuits. So we decided to go ahead and put out the effort so that we could do something further with this afterwards. Okay, so this just shows you the parameter space. Nobody cares. So here is a typical result. And so I have to explain what all these are. I showed you that movie showing how the phase of the wave function evolves in time. And each one of these pictures is the last frame of that movie. So after 4,000 milliseconds of system evolution time, here the length of in this particular case, the length parameter is 30 micrometers, and this TR is essentially a measure of the speed. TR of 6 means that if I stirred the ring for 4 seconds, it'd go around 6 times. So it's just a scaling. And then this little number here is the energy height of the barrier. So in the units of the chemical potential of the condensate. The chemical potential is the energy required to add one more particle to the condensate. And so this is half of the chemical potential of the unstirred condensate, up to 2 times the chemical potential. And you can see everywhere we have a rainbow, we got flow. Okay, so you can look here at the beginning, you can see 0.5 and 0.2, all these things all the way up on the top row, there was no flow. We were stirring it strong with a stronger and stronger paddle. I tried thinking of a way of an analog of that, and the best I could come up with was taking a stick and drilling a bunch of holes in it. So if you have a bunch of holes in your stick and you stir it like that, it's not very good at producing flow. And so the higher this is, the fewer holes are that are in your stick. Okay, how about that? It's not perfect, but you get the idea. And so you can see here that as we stir with a stronger and stronger paddle, we start to get flow. So down here we have no units of flow at the end. This is at the end of each of 4 seconds. And down here at two times the chemical potential, we get, you can just count the red spots or the blue spots, whichever is easier. You can see we get 3 units of flow. And, but buried in here is something very strange. You would have thought that the amount of flow that you get increased monotonically as your paddle was stronger and stronger, but it doesn't. And so here up in the corner shows here is the x-axis here are these numbers on top here, from 0.5 up to 2. And the vertical axis is essentially a number of red spots, if you like. So here you can see that the top row here, you get nothing. And then suddenly you get 2. This is also another interesting point, is that this jump in energy high from 0.68 to 0.7 times the chemical potential, is a teeny tiny little energy jump, but it produces 2 units of flow. So maybe somewhere in between 0.68 and 0.7, there you get 1 unit of flow. But so far, we haven't been able to find it. And so you can see here it's 0, and then it's 2, and then it's 3, and then it's 2 and 3, and it bounces back and forth as I stir with a stronger and stronger paddle, all other things being equal. So the reason for this, I can tell you very easily. I don't know. This is still a mystery to us. This is one of the goals of this simulation, of this set of simulations, is to come up with a simple model of how, because this would be very handy if we were designing an atomtronic circuit to know, say, okay, we want this many units of flow, how should we stir it? If we had a simple model that would tell us that, then we'd be able to design these things much more easily. And I can give you the punchline on that is that we haven't come up with something simple yet. You could do a 12-hour simulation for each one of these to find out what flow you would get, but that's not really practical. Okay, and so we did so I just want to run through these. I want to run through this set of results, but this, whoops, here. So all these, each one of these things is like that one. And therefore, there are the 4 different speeds for L equals 0 micrometers. So that's the ring. You can see that, obviously, if I stir faster, I get more flow. You can look down here, slow stir, down here, fast stir, I get a lot more. So that's pretty obvious. And then another interesting thing, I'm going to flash through 0, 10, 20, 30, 40, 50, 60, 70 micrometer, up to 60, not 70, 0 through 60 in jumps of 10 micrometers. You'll see that the more elongated the racetrack is, the more flow I get. So you can see 0, 10, 20, 30, 40, 50, 60. You can see in 60, there's much more. You just have to count these red spots here. Down here, it's like 8 and 9. But we never, even for elongated racetracks, we still find that these things oscillate. We don't know. Okay, so, but one thing we have learned is that, which we kind of knew, and this is what was, when you stir, you know, if you fill up your bathtub with water and you take like a stick and you pull the stick through the water, you'll spawn off these vortices in the water. And you get vortices here too. And I'm going to show you we decided to look at this more. Oh, yes, here we are. Actually, I have no idea what this is. Yeah, okay. So this shows you the full simulation. And then I can come over here and show you just the first 10 frames. There. So here, bonk, bonk. Frame 3, frame 4, frame 5, and then 6, you get flow, and 8, 7, and 8. So what we decided to do was to do a slow motion. And so let me go back here. A slow motion between frame 6 and frame 7. So we had a full 100 frames in between those 2 frames of the full simulation. And at that time, the barrier is over here. And so you're just gonna see a blow up of this bit of it in the next. So that's what this is. This is a blow up. And this is the velocity distribution. And this will be the vorticity. The vorticity is the current curl of the velocity distribution. So if I have a vortex, this will pick it out. And so this actually is a spike that's positive, and this is a negative spike. And this corresponds to, you can kind of see over here, if you see that, that's in this third box here. See the third box? We cut this off over here because there are no atoms over there. But you can see that there's kind of the velocity vectors are swirling around this way. So that guy, the red guy is counterclockwise swirl around, and the blue is the other way. Okay, so now I'm going to try to play this movie. Okay, so I'm going to play the velocity distribution, which is really great. Okay, let's try it again. Try one more time. Yeah, they'll both play at the same time. That's good. So you can see here that what's going to happen is that there's this vortex. This is a vortex. That's a vortex. It's going to exchange. It's going to send a vortex over. And then boom, after that, there's flow. So we got this. We decided to do this sort of drilling deep down into the results just recently. So we still don't understand what it's doing exactly. But it's quite this. I put this in to illustrate that studying the vortex motion is the thing that's going to be key in understanding how we get flow. I also put it in because it kind of looks cool. Yeah, so I'm gonna skip over this stuff because I want to. Let's see how much time I got. How much time do I have? Ooh, almost no time. Okay. Well, I'm going to get to this. I can skip over this stuff. We also have looked at stirring at non-zero temperature. We use this thing called the ZNG model. So basically in the ZNG model, you have a condensate and you have a non-condensate. The condensate's treated just like the condensate at zero temperature was, but there's a term in it that allows atoms to exchange back and forth between it and the non-condensate. And the non-condensate evolution is described by the Boltzmann equation. So here's this is the GP equation, the generalized Gross-Piasecki equation. But you can see if you throw out those two terms, then it's like the zero temperature thing. This N-tilde does the non-condensate density, and this thing here lets you exchange, lets the condensate gain and lose atoms to the non-condensate. But the ZNG model fixes the total number of atoms. Condensate plus non-condensate is fixed. So the non-condensate, so I want to be very brief. The Boltzmann equation solution is something we call the single particle distribution function, and it means that if you multiply if you evaluate this function at some momentum and some position and at some time, multiplied by the phase space volume element, you'll get the number of particles that have this momentum and that position at that time. And so if you can add up all the momenta at the same position, and it gives you the non-condensate density. Okay, so first thing we did was we calculated the condensate fraction as a function of temperature for several different racetrack lengths. So Z and G is much more difficult and complicated to solve than the zero temperature model. So we didn't do as all this number of cases that we did for the zero temperature, but we still did a boatload of cases. But you can see here that one of the things, so this shows you the condensate fraction. This is the number in the condensate divided by the total number. And on this axis is the temperature in nanokelvin. And here, this is for the L = 0 racetrack, the ring. This is for 30 micrometers, and this is, so we've got one that's a ring, one that's kind of medium sized, one that's really elongated. And so you can see that we calculated these 3 points and then fit it to a 1 minus T/Tc to the alpha. That's the red curve. So we are able to look at a case where it's mostly condensate and another case where it's about half and half. So then, okay, so here I'm going to show you, so this is again the zero temperature thing for 30 micrometers and that speed of stirring. And then I'm just going to flip through and show you that this is the same thing at 100 nanokelvin. And here it's 150 and there it's 200. And so the main thing, I'm going to go back here. In the interest of time, I'm just going to tell you that the punchline for the non-zero temperature is that all of these strange things that we see at zero temperature persist, except that the temperature, the main effect of finite temperature is that it depletes the condensate, given that you're fixing the total number. And so this changes the quantitative stuff, but the qualitative stuff is the same at finite temperature. So I'm going to put my conclusions up on the board, and thank you for your attention. Yeah.